Okay, good. So, we're ready to start the first after coffee session. And we have the pleasure of having Mike Green, who will tell us about multi-loop systematics in pure spinor field theory. Please, Mike.
Well, it's a great pleasure to be back in this very beautiful city. So the subject I'm going to talk about is based on work done in collaboration with Jonas Björnsson, who is in the audience somewhere, and who not only did the larger part of the work, but has the virtue of being Swedish, so he comes from near here. The motivation for this work is based on trying to understand aspects of work that's been going on in all sorts of places in trying to construct scattering amplitudes and perturbation theory in field theory, mostly with the most complete being in the maximally supersymmetric field theories, Yang-Mills and supergravity. And there's been heroic work, particularly by people I will talk about later, who have calculated 4-point amplitudes up to, so far, up to 4 loops with some partial results at 5 loops. However, throughout this work, it's always seemed peculiar because, after all, these are theories which are, in some sense, contained within string theory, and we have a good understanding of how to construct loop amplitudes in string theory. And there, the situation is relatively simple, even though if you ask precise questions, it might be rather difficult to get precise answers. But at least we have a rather beautiful geometric understanding of the structure of the perturbation expansion. And in some sense, the ordinary field theory should emerge at least in some limit. So that was the motivation. That's not precisely what I'm going to talk about, but that's in the back of my mind. So let me just remind you very quickly of the situation in these very supersymmetric theories. Yang-Mills theory in 4 dimensions, of course, is ultraviolet finite, and maximally supersymmetric Yang-Mills is. But you can ask interesting questions about the systematics of the ultraviolet divergences in higher dimensions as a function of the number of loops and as a function of the colors. So, for example, we know that that at 2 loops and beyond, to all loops, there is a term of the form d squared trace f to the 4th in Yang-Mills theory, but d squared trace f squared squared doesn't get renormalized beyond 2 loops. So that's one example of an interesting statement. This is in any dimension. In supergravity, the calculations are even more difficult because those are essentially as difficult as doing the full non-planar Yang-Mills theory. And as most of you know, this has been pushed to a large extent by this group of people, often called Baird et al. And we hear rumors from somewhere in America, on the West Coast, all the time about proceeding towards 5-loop calculations, but so far, as far as I know, there are no concrete results. There are indications based on the use of supersymmetry to analyze possible counterterms that there ought to be or there could well be a problem when you get to an interaction of the form d to the 8th r to the 4th. This would arise, for example, in 4 dimensions, n equals 8 supergravity. This would arise as a 7-loop counterterm. And there are a number of arguments, mostly based on analyzing possible counterterms that are consistent with the global E7 symmetry of the theory, and also, to a certain extent, based on string theory arguments for why that might arise. And then there are arguments, mostly by Renata Kalash, for why it might not arise. So there is an issue about whether or not this d to the 8th r to the 4th interaction is going to cause a problem. So that's the background to the supersymmetric field theory calculations. Now, in string theory, one can, as I said before, at least write down formal expressions for the loop amplitudes in a very efficient way, either in the Ramond-Nevers-Schwarz or the pure spinor formalism. The pure spinor formalism, which is what I'm going to talk about today, was of course pioneered and to a very large extent carried out by Nathan Berkowitz over many years. And although it has technical problems, which I shall allude to but won't resolve later on in this talk, it nevertheless has some extremely attractive features, not the least being that all the calculations emphasize the space-time supersymmetry of the theory, which is something that is lacking in the other ways of calculating the loop amplitudes. So the reason why progress has perhaps been slow using traditional methods or using the efficient methods of the Bern-et-al. Group is that they don't build in supersymmetry, and one doesn't know a priori how much supersymmetry is constraining the answer. There have been limited number of calculations using the pure spinor formalism in string theory, but those that there have been very impressive. So there are some 1- and 2-loop calculations, and recently a very elegant-looking multi-particle tree-level calculation. So I'm going to try and abstract from the string theory some of the contents of the pure spinor approach to string theory, and try and implement them in field theory. And this talk will have, by necessity, be very sketchy, in fact, extremely sketchy. But the idea will be to try and abstract the aspects that make the supersymmetry manifest and try and implement them in field theory language, partly to satisfy the usual reply of people who hear about pure spinor field theory, string theory, and hear about how efficient it is, and then their reaction is, well, that's string theory, isn't it? As if it was not field theory. So the motivation, the direct motivation here was to try and adapt some of the language of the pure spinor formalism into field theory. And I will talk about the ultraviolet divergences of loop amplitudes, and I will explain how you can see, just by counting fermionic modes, that the results that Bern-et-al. Have got, at least that limited set of their results, can be explained simply by fermionic mode counting, which originates in the supersymmetry. And then I will say something about going beyond 4 loops, and I'll show you an explicit suggestion for what happens at 5 loops, although that's where some technical difficulties are met, and therefore it is not a conclusive result. So the slogan for the talk is, this is modeled closely on the pure spinor string, and that means, unfortunately, that I have to introduce, but sketchily, some notation. If you don't want to watch the notation, I will have pictures at the end, which are self-contained in some sense. So what is the theory? Well, it's basically looking at the 0 modes of the pure spinor string, and there are 2 versions on the market, but the second version, the first one's the so-called minimal version, which adapts the supersymmetric particle action. Theta is the supercoordinate, of course, and x is the space-time coordinate. It adapts it by introducing this pure spinor, so-called pure spinor ghost lambda, and its conjugate omega. But the non-minimal version is the one which is best suited for talking about multi-loop diagrams, and that has some extra 4 coordinates, which form a sort of package of bosons and fermions. And the idea is to mimic the string theory by looking at the first quantized world line version of multi-loop diagrams, which is manifestly space-time symmetric. I've put a comment here. Of course, the pure spinor string emerged out of Nathan's mind in a way which seems to work, but its origins in sort of a logical geometric understanding are still somewhat mysterious, although there are recent ideas which look, to me, possibly interesting. So these coordinates that enter the action consist of bosons and fermions, and I've listed them here because I want to just make a note of the number of components. We're talking about a theory, we're formulating in 10 dimensions just for convenience, for packaging the for the notational convenience. Of course, we're going to think of it compactified. This is field theory, and we're going to compactify to an arbitrary dimension later, just to talk about the theory in lower dimensions. The non-minimal coordinates are the ones on the right, and the pure spinor constraint, which I've listed here, reduces, the lambda would have been a 16-component spinor were it not for that constraint, but this reduces, so the lambda is constrained by these conditions, and lambda bar and r likewise. The conjugate momenta are world line vectors, and so the number of components is proportional to the number of loops. This is, I'm going to go through a rather delicate mode counting argument later, where I'm going to have to saturate the fermionic zero modes, and so that the fact that there are L modes for each world line vector is important. And in writing down the supergravity version of this, one doubles all these fields. So these fields are, for convenience, simply the ones that will come into the Yang-Mills version, but the hatted ones, and I will be talking about gravity mainly, the hatted ones will come into the gravity version. One defines a BRST operator for each sector, the unhatted and hatted sectors. That's the Yang-Mills BRST operator, and then the supergravity operator is the sum of them. And one also defines, now there is no BC ghost in this system. This is a bit like a topological string theory, but there is an object that plays the role of the BC ghost, of the B ghost, which Nathan discovered in early on, which is a composite object which looks at first sight very complicated, and it looks even more complicated at second sight, unfortunately. But it's, so I'm just writing down some of its features. There's some dots here for terms which I won't talk about in this talk, but need to be taken into consideration in detail. The important thing for this talk is to realize that there's the first term has one D is a fermion, has one D coordinate in it, and one momentum coordinate, P, while the second term has two Ds. And that's the thing to remember. That's all you need to remember about the B ghost. And it also has inverse powers of lambda, and those are the things which can cause a problem. So the more B's you need to have in a diagram, which means the higher number of loops you go to, the more inverse powers of lambda, and there will come a point where there will be too many inverse powers of lambda, there will be a singularity at the origin, and that's where some trouble occurs. But for the moment, let me just go on and well, of course, there's a B hat ghost, which is exactly the same, defined in terms of the hatted fields. So we want to construct amplitudes, tree level and loop. I won't talk about the trees here, but looking at loops, so here's an example of a two-loop diagram. So the way the loops are constructed is by writing down all the possible skeleton diagrams. These are the phi-cubed vacuum diagrams that you can draw, and labeling them with their loops and cycles. And in general, there will be 3L minus 3 propagators for an L loop diagram. These are basically their lengths are essentially the moduli for the loop. So this is all analogous to what you know about for the string. You can define a basis of one forms for expanding vectors and tensors on these loops, and something which is essentially the period matrix, which is defined with respect to the cycles that you have. This looks like a string worldsheet diagram in which you've shrunk the A cycles away, and it only has the B cycles. And so here's an example of a period matrix. Now, the secret of what I'm going to say resides in what I said before about the B ghost having those terms, and also the structure of the period matrix. So the period matrix encodes the nature of the diagram we're talking about. And that plays an absolutely central role in determining the contributions of these diagrams. So the amplitude is written as a sum of all possible skeleton diagrams to which you attach vertices. So this is an integral over the moduli for the skeleton. And then this function k is a function of where you've attached the vertices and the momenta. And this is just like a string amplitude. You have a measure factor. There's a regulator, which needs to be discussed in a second. And there are B-ghost insertions that are important for reasons which are the same as in string theory. And then there's a product of the vertex operators attached to the lines weighted with the exponential of the action. So the main thing that I'm going to talk about is how the fermionic zero modes are saturated. And where do they come from? Well, they come from the vertex operators. This regulator, which I'll describe in a second, also has them. This regulates without the regulator, the integral over lambda, which is hidden in this measure, would diverge at large lambda. There's no cutoff on the large lambda behavior. So this regulator regulates it. And also regulates a zero that comes from a fermionic integral that I'll mention in a second. And then the B ghost also contains zero modes. So there's an interplay between the zero modes of the fermions that occur in these three places. So let me very rapidly mention the vertex operators. So the vertex operators, again, are essentially the zero modes of the vertex operators in string theory. You can have an unintegrated vertex operator, which is this thing A. So A is a superfield, which in this is the gravity case I'm talking about here. There's a hatted and unhatted lambda multiplying it. So an A contains within its theta expansion the curvature tensor in the cubic term. And the integrated vertex operators contain a number of terms, of which I've shown, again, only the ones that I'm going to mention. Here, the vertex operators contain two terms. The two terms I'm showing are the ones which have two momentum factors multiplying what is essentially the metric superfield, and another term which has two d mode, one left and one right moving, or one d and one d hat d mode, multiplying a bispinor superfield. And these superfields are required to satisfy the field equation, the linearized field equations, and that's a consequence, although I'm not going to prove it, that's a consequence of requiring the formalism to be invariant under BRST transformations. The second of those three items I wanted to mention is this regulator. So N regulates the apparent divergence at large lambda, but there's another problem also that it regulates simultaneously, which is the fact that this S fermion, it doesn't appear in anything I've written so far. So if you were to integrate over the S fermions, you get zero. So there's actually a zero over zero problem, zero from the fermions, infinity from the large lambda, and this regulator is a completely standard way of regulating divergence of this sort, or ambiguities of this sort, by exponentiating a BRST exact function. So the fact that it's BRST exact means that you can prove that you can put an arbitrary coefficient, which I haven't done, in the exponent, and nothing depends on that coefficient. I just noted that theta occurs multiplying r. So when you have powers of r and you integrate over r is a fermion, you will bring down powers of theta, and that's where some covariant derivatives that arise will come in later. And I've also noted that the only source of S in the whole expression is in this exponential. That means that when you integrate over the 11 components of S, you have to pull down 11 powers of lambda and d at the same time. And since S is a world line vector, actually there are 11 L zero modes. So that's very important for the mode counting. That putting out 11 L zero modes of S brings down 11 L zero modes of D, and but D actually has 16 L zero modes in all. So you've used up 11 L of them. You've got 5 L more to find from somewhere. So there are 5 L that have to be found, and this is another sort of slogan. Where can you find the 5 L D zero modes? They have to come either from the B insertions that I've already mentioned or the vertex operators. Now the B insertions, now you have to go back to B I emphasized two terms. One of them had a couple of D's in it. Let me just perhaps take you back there. So B has two terms. The second term is the one which has a maximum number of D's. And it's important in this counting that, well, you can organize the counting in many different ways. One very efficient way of organizing it is to first consider having as many D's as possible coming out of the B modes. Well, that means taking the term that I just mentioned, so what I've written down here is the zero mode of B, and you can you can expand the zero mode of B and show that that term, which is quadratic in D's, it multiplies a derivative of the period matrix with respect to the modulus so I'm integrating this over one of the lines with modulus Ti, and this is the expression you get. And so when you have to insert 3L minus 3 factors like this, and that would insert 3L minus 3 times 2 D modes, D zero modes. But there are restrictions on whether or not you can do that, because d omega by dt depends on what diagram you're talking about. I think, rather than make the statement, I'll show you an example later. But the shape of the diagram determines whether or not you can really soak up that many D modes from the insertions. And that's where the restrictions come from. There is an issue which I will skip over. The formalism is set up as an ansatz, if you like, and then you have to check that BRST invariance is satisfied by seeing whether BRST exact vertices decouple in the way they should. And you find that they don't, unless that you have to add certain contact terms in order to make them decouple. Now, Jonas did this part of the work in a rather technically complicated enterprise, so I certainly can't go through it. But let me just say, to summarize, that the skeleton diagram has cubic vertices, and that's all you need all the time. But on the exterior of the diagram, where the exterior vertices are, then one needs to add, in certain cases, when you get to high enough ordered loops, you have to add contact terms of the type that might be intuitively obvious from Yang-Mills theory and supergravity. So let me now consider the scattering amplitudes, having rushed through the formalism. At one loop, you need to have one unintegrated vertex operator, which I've indicated by a cross, and 3 integrated ones, and then you simply reproduce the usual divergent term, divergent in more than 8 dimensions. So the dimension that we're interested in, that I'm going to emphasize, is the dimension in which there's a log divergence, which is 8 dimensions. This is, of course, a very old result, but the way the answer comes out here can be expressed in many ways, but one way is to say this is 2 covariant derivatives to the power 8 acting on the metric. And when you count the thetas that way, you see that it's a half BPS. So the virtue of this is you can see the BPS nature of the interactions coming straight out because everything is supersymmetric. And I'm putting brackets the Yang-Mills case, but I won't emphasize that. Now here's 2 loops. Also, this is an old calculation of done the other way, done the usual way, and it's well known that there are 2 contributions that come in. The points here are the distribution of the integrated vertex operators. The black dots are always the vertex operators involving 2 D modes. And the rule is that you take a skeleton, and if it's got, in this case, 2 bubbles, 2 loops, each loop only has 2 lines on it, you have to put 2 more dots on each loop because you have to have at least 4 lines in every loop, otherwise the diagram will vanish. I'm just quoting a result that comes from this fermionic saturation. So these diagrams are allowed, but this one isn't, because the right-hand loop doesn't have 4 propagators. It's only got 3 propagators. So that explains, in some sense, why those people only ever find those first 2 contributions. And the answer here comes out in a way which makes it manifest that it's a quarter BPS, and it's logarithmically divergent in 7 dimensions, which is well known. And it turns out, although this is not really relevant for this talk, that the coefficient of that divergence is proportional to the vacuum amplitude of phi cube field theory, actually, in 4 less dimensions, in 3 dimensions. The log comes in at 3 plus epsilon dimensions. At 3 loops, well, here's the first case where there are 2 distinct shapes for the skeleton diagrams, and therefore 2 distinct period matrices. And this illustrates what I was saying before. The first period matrix for this loop is degenerate. There's a 0 in the top right-hand corner, which also signifies that this only involves 5 linear combinations of the moduli, whereas there are 6 moduli. It depends on T5 plus T6, but not T5 minus T6. And this makes the mode counting change in the way I intimated before. And this changes the behavior of the diagram relative to the second diagram, which is not degenerate. So now you contemplate adding dots to these diagrams, and you find that essentially because of that pyramid matrix structure, the only configurations you can have are ones where you put 2 dots on each of the outlying loops. There are other ways you can put. This is only one diagram of several. But these diagrams give a non-leading divergence. These diverge in some peculiar number of dimensions, but this is proportional to, actually, I think it should say d to the 10 out of the 4th. I'm sorry, that's a mistake. This diagram is not allowed, and essentially because the left-hand loop only has 3 propagators instead of 4. But this one is allowed. This is an example of allowed one. I've only put 3 propagators, three vertices there, because now, instead of having just the second part, the vertices which have 2 Ds in them, you can put the vertex which has a p squared in it. And that's the leading, the p is the internal momentum, essentially. So this puts a p squared in the numerator internally, and this diagram is now more divergent than it would have been if we hadn't used that vertex. So this is more divergent. Here's another contribution. And there are other contributions I'm not mentioning. But all of these are more divergent than the ladder diagram, and it's logarithmically divergent in 6 dimensions, and it's an 8th BPS. It comes out as some 14 covariant derivatives on the metric. So that's the 3 loop. Maybe I'll skip over that. 4 loops. So I'm not going to go through the complete calculation. 4 loops, there are now 5 different skeletons. So you have to work out the period matrix for each of those, work out how to saturate the 0 modes, and then you find that the most divergent piece. Oh, sorry, no, this is the one which is wrong. Yeah, that should say d to the 12th out of the 4th, I think. Anyway, it diverges like lambda to the 4d minus 26. And that's the most divergent piece. The least divergent piece is a diagram like this, because now, instead of just one of those p-squared vertices, you can put 2 p-squared vertices in, and that's the most divergent contribution. And putting p-squared in the numerator, of course, causes some vertices. When you evaluate these integrals, it causes certain propagators to collapse. And so these diagrams, which have these white blobs, sometimes look like as though they have contact terms in them. And in addition, I haven't mentioned, well, in the Yang-Mills case, the fact that you have diagrams which do have the contact vertices I mentioned earlier. But in the end, one gets a picture where these diagrams match, at least, I'm not sure that we've matched them in detail, partly because it's horrendously difficult work, but they match, at least in structure, the diagrams that end up in the Bernoulli, in this field theory calculation, being obtained, but in that case, they're only obtained after huge numbers of cancellations. So at 4 loops, for example, you have to work quite hard to show that the leading contribution is d to the 8th out of the 4th, because superficially, it looks as though it's a lower power of d. But then there are lots of cancellations that occur that appear miraculous within that formalism, but in this formalism are just a natural consequence of supersymmetry. This has a log divergence in 11½ dimensions. So at this point, the agreement, of course, the agreement is qualitative because those people who did the calculations using field theory have worked very hard for many years and come up, of course, with the precise detailed coefficients. We haven't calculated the overall coefficients of these diagrams, and so, but the agreement is in structure with the statements that up to and including 4 loops, both in Yang-Mills and supergravity, the first logarithmic divergence occurs in this dimension, 4 plus 6 over L. If this was true to all orders, then of course when L goes to infinity, you would see that d equals 4 was the asymptotic value at which there was no divergence, and the theory would be finite. So the issue is, does it continue to all orders? And of course, that means that one should go to higher order to find out. The next order being 5 loops. So 5 loops, as far as I know, almost nothing is known concretely in any formalism. But let me just show you some pictures. So at 5 loops, it's very easy to draw the skeletons. So now there are more skeletons. And these are all the possible skeletons that you can get at 5 loops. But there's something rather special about them. If you loop at them all, you will see that only the last 2 are ones which have no triangles. And so one can argue that the first 14 of them are not, well, one has to put these vertices that have d's in them instead of p-squareds, so that, that they are less divergent. The first 14 of them are less divergent than the last 2. So the question is, are the last 2, what's the structure of the last 2? And they are very special, and unfortunately they're special in a bad way as well as a good way. They're special because this is the first time where one encounters a power of lambda bar, which is a 12 inverse power. And I may not have emphasized it, but 11 inverse powers is where you start to get a logarithmic singularity from the small lambda end of the integration range. So this is got a new divergence. Furthermore, they're 12 powers of r, but there are only 11 independent r's. And so there's a 0 over 0 problem. This was addressed in a very, I guess, nice but difficult paper by Berkowitz and Nekrasov, who have a way of regulating this divergence that we have made minimal use of because we don't really understand it. And I asked Nathan at the coffee time about it, and I'm not sure he really understands it. So, well, he understands it, I'm sure, but I'm not sure he could do a specific calculation using it. I mean, it's one thing to understand it, and another to actually have an algorithm for using it to do a calculation. So let's hope that it's a sensible regulator. If it is, then I will, since time is running short, paraphrase the argument, but simply say that, then the naive mode counting says that for this case, for the first time, when you construct an amplitude, you need only use the most singular part of the vertex, the p-squared part of the vertex, the white dots. And there are only these 2 contributions that come in. These are the maximally divergent contributions. And they diverge like lambda to the 5d minus 24. And that's naive dimensional counting. The point is these white dots contain p-squareds. P with an index. P is a vector, so the p times p. But it turns out that actually the white dots literally cancel the propagators they're sitting next to. So that the result of this planar diagram, for example, is literally a vacuum diagram for this 5-loop phi-cubed process. And a vacuum diagram is simply given by this expression. And you can see in your heads that this diverges logarithmically when 5d is equal to 24. Now, there was this proviso that we don't really understand the role of the regulator here, so that we're uncertain about how to calculate this coefficient C5 in any case, and we certainly haven't done it. It's conceivable that it could vanish, I suppose, when you add the 2 contributions together. But this will be the first time that there's a vanishing which goes beyond what we would normally think of as being supersymmetry. In all the previous cases where there were vanishings because of cancellations in the Feynman diagram way of doing things, those came out with their leading ultraviolet behavior coming out of each diagram separately. But here there would have to be a cancellation. So the suggestion is that this is an explicit 5-loop contribution to d to the 8th r to the 4th. Now, d to the 8th r to the 4th would have had to be non-renormalized at 5 loops if the other counting was correct. If this formula d equals 4 plus 6 over L was correct, then d would be 26 over 5, because in fact, that formula would work if you put out an extra factor of d squared for each loop. If you go down to 4 dimensions, then it's easy to see, and it's also easy to argue that what I said continues to all loops. Once you've got d to the 8th r to the 4th coming in at 5 loops, it would also come in at 6 loops, 7 loops, and so on. And in particular, at 7 loops, this would give rise in 4 dimensions to a logarithmic divergence, or a d to the 8th r to the 4th counter term, which is the one I was telling you right at the beginning was expected to be there for various other reasons. And therefore, I mean, the surprising thing that happened would be if that coefficient vanished, although I don't think there's any obvious, well, there's no obvious supersymmetry protection. I say obvious because I mean, if it did vanish, there would presumably have to be some deep reason for it, but we don't know why it should. So all that does is emphasize that this is an incomplete calculation of a 5-loop diagram. It's probably the most complete calculation there is, but it's very incomplete. It will be very interesting to see what its divergence is. Let me end by just raising some obvious questions. But coming at this from string theory, of course, one asks, why on earth is this of any interest, since supergravity is only a piece of string theory? Well, it would, of course, be interesting if the divergences did vanish. Well, one would then be led to ask whether there was any meaning to what you got out, because it ignores all the other structure in string theory. But more specifically, if there were ultraviolet divergences in field theory, since there are none in perturbative string theory, surely there should be some cleverer way of doing the field theory where you start with the string theory and take a limit. And that's actually where I started thinking about this and really have not got very far. What I've talked about was modeled on the string theory calculation, but was most certainly not directly taking a limit from the string theory. And then sort of a gratuitous point that string theory has these wonderful and rich dualities which are absent in perturbative supergravity, and somewhere or other lurking in the background there ought to be some reason for why the supergravity is either finite or not finite. Thank you.
Questions? Yes, Martin?
Is it easy to see why this mechanism doesn't mess up the Yang-Mills theory?
Doesn't mess it up? But sorry, Yang-Mills theory in 4 dimensions, of course, doesn't have ultraviolet divergence.
Can you speak up, Martin? Repeat the question.
Oh, yeah, but the audience may not have heard it. So, let me repeat the question. The question was, if I got it right, why doesn't this counting or this procedure mess up known results in Yang-Mills theory? Is that right? But I mean, what I was saying is it confirms the known results in Yang-Mills theory. And well, in particular, something I skipped over at my transparencies is there's a distinction, for example, in the color dependence of these amplitudes. Well, I mentioned it at the beginning, actually. I mentioned that as a result of one, you can argue that from supersymmetry. But for example, the d squared trace f to the 4th interaction behaves differently from the trace f squared squared piece. And that comes out of this, that we can see.
Please.
In the RNS formalism, there have been some recent progress in, by imposing modular invariance and so on, but they also seem to have difficulties at 5 loops. So there's the uniqueness in the vacuum in the measure sort of stops at 4 loops. You think there may be a connection?
Whose work is that?
I think these are some mathematicians. I forgot.
Oh, I know about it.
And in the US also.
I know insufficient. I've seen the references.
Okay. Please speak up.
Suppose I give you some skeleton diagram with, let's say, 3, 4, and 5 loops. How uniquely can you tell me which part of the spinor computation this belongs to? Is it possible to...
So say that again?
Suppose I give you a certain skeleton diagram, and can you uniquely tell me which part of the spinor computation it belongs to? Some hyper-priori dictionary?
So if given a skeleton, which defines the period matrix, then I can do the counting I described, and depending on where I put the vertices, you have to integrate over all possible positions for these vertices around the skeleton. But in some domains, you will simply get 0 because you'll be killed by fermionic 0 modes. So the particular diagrams I drew were examples, some of which were non-zero, and then others were 0 because of that. I'm not sure that was your question.
Is it unique?
Unique. It's unique within the formulas. I didn't actually show you the formula for how you associate an actual expression for an amplitude with a given skeleton. But with that, it's unique. In other words, up to partial integrations. I mean, there are ways of re-expressing the amplitudes by doing partial integrations all over the place. But within our particular scheme, if you like, it's unique.
Can you then reconstruct the propagator structure of the diagram from the spinor computation?
But it contains, I mean, the diagrams have the propagators and vertices. You essentially construct them by tying them together. This is, I mean, it's a first quantized picture of what these diagrams are. So.
More questions? I'll try to pass you the mic. One moment. Can you pass this down?
So, I mean, in this first quantized formalism, do you have all the complicated vertices of supergravity? Or is there somehow just cubic interactions?
Well, in the interior of the diagram, it's just cubic. And you can show, I had a picture which unfortunately I deleted because the talk was too long. You can show by moving the BRST charge around that so long as, when you sum over the skeletons, you sum over internal 4-point functions in all channel, with poles in each channel, then there is no problem, there are no contact terms internally. But on the boundary, essentially because external vertices collide, you get effective contact terms. Let me just... which don't affect, they don't affect the asymptotic behavior, the leading divergence of the supergravity, but they do, in the Yang-Mills, they're crucial. So here, this is a poor attempt at the caricature of such a contact term. So here's a 4-point function with 2 dots representing the vertices I talked about before, and then this is a new vertex, a contact vertex. Its form, this is what I referred to before when I referred to Bjornson, its form is determined by requiring BRST invariance. So you put a BRST trivial vertex on the outside, move Q around, and try to show it vanishes, and you get hung up on places where vertices collide, and you have to cancel. And there's a sort of an iterative procedure where you can cancel that by adding a contact term.
Well, I don't really understand the formalism, but somehow the external gravitons or gluons were connected to this diagram. But you seem to be able to get rid of that and reduce to a skeleton diagram in 5-4 theory.
Well, I can get rid of it at low orders. Sorry, on the outside, not...
Well, when you actually calculate the graph,
Yes.
there would be external lines attached, and there would be more propagators. But somehow all that went away, in your lecture at least.
So this is where the external lines are attached, the on-shell lines, you mean?
Yes?
Well, I'm saying there are contact terms which you have to add, but their contribution vanishes at low numbers of loops.
Okay. Sorry, your dots originated as insertion points of the external lines?
Yes, I should have.
Okay,
yeah.
you probably said that properly. Okay.
Okay, so I think it's time to move on. So let's thank Mike once more. And we carry on.